Hello, welcome to STEMist. Today we'll be talking about a theorem in a realm of number theory, the Chinese remainder theorem. On a side note, I know number theory damages our brain cells and we don't talk about them in high school, but you are gonna bear with me today because you are smart. Anyways, as the name suggests, the Chinese remainder theorem was devised by Chinese philosophers. Sun Tzu in the 3rd century CE, this guy right here, proposed the first known statement of the theorem, although its completed version was not given until 1247 by Qin Jiushao. Yep, this guy here, and hopefully I pronounced his name right. The theorem concerns itself with solving congruences of the first degree, which was originally used in ancient China to calculate calendars. See how smart the ancient people were? You couldn't even count days if you didn't know these fancy theorems. No pressure though. If you don't know what congruences and modular arithmetics are, no worries. I'll make another video to explain that. Now, let's get into the topic. First, I'll let you stare at a theorem for 10 seconds, or pause the video if you need to, if you're the kind of genius that figures everything out by yourself. And bear with my handwriting here. The description is pretty clear. The same number x has congruences a1 to ak, modulus n1 to nk. n1 to nk are pairwise coprime, meaning that if we take two random ni and nj out, it doesn't matter which pair I choose. They are not going to have any common factors except for one. a1 to an are arbitrary integers, meaning that they have no special properties. If a system of simultaneous congruences satisfies all these conditions, there is a solution for x, and the solution is the unique modulo capital N. We define this capital N to be the product of all the simultaneous modulus 1 and 1 to nk. Alright, now hopefully you have a basic idea of how it works. But why on earth does it make sense, you must wonder? Okay, let's talk about a proof then. How we're going to prove it is by finding the solution to the system, then prove that it is the correct and only solution. So first, let's find the solution to this congruent system. As we defined earlier, capital N will be the product of all the little ni's, n1 to nk. Now for each I equals 1 to k, we define yi as capital N over ni. They are equal to the product of all the little n's from n1 to nk except for ni itself. Note that this yi is coprime to ni because all the n's are pairwise coprime and ni is the only factor in capital N that can divide itself. So when this ni is the denominator, aka taken out from the capital N, there will be no n's left in capital N that has a common factor with the little ni. Because ni and yi are coprime, we're able to find the modulo inverse of yi mod ni, and we name the inverse zi. As per definition of a modulo inverse, zi times yi is congruent to 1 mod ni. It also follows that zi times yi is congruent to 0 mod nj, where j does not equal I. This is because yi contains all the little n's in capital N except for ni, so each of these nj's can all divide yi and its product with zi. Lastly, we find a product of ai, yi, and zi for all the i's and compute their sum. This sum is the solution to the congruent system. Wow. Are you still following? I totally understand that can be a bit confusing. So why is that the correct solution? Well, let's see if the solution satisfies our initial conditions, which is that x has congruences a1 to ak modulus n1 to nk. Since our x is sigma ai times yi times zi for all the i's from 1 to k. Well, if you don't know what sigma is, I'll make other videos to explain it. Anyways, if we're to take any value in the range of i's, things like n1 or n13, and calculate our modulos, we'll always get this. 0 plus zeros plus a bunch of zeros plus ai times y times zi plus a bunch of other zeros. This is because what we have already proved a minute ago. For any j that's not equal to I, the product of aj and yj is congruent to 0 mod ni. Then if you are familiar with the multiplication rules of modular arithmetics, it is pretty intuitive that the product of aj, yj, and zj is also congruent to 0 mod ni. For example, when I equals 13, n13 will divide all the terms in x, aka all the aj times yj times zj's where j is not I, where j is not 13, resulting in a bunch of zeros modulo n13, except for a13, y13, z13. So, what is a13 times y13 times z13 mod n13? We already proved that yi times zi is congruent to 1 mod ni. So a13, y13, z13 mod n13 is basically n13 times 1 mod n13, which is n13, which is exactly our condition. We can try this for every I from n1 to nk and it will all be true. Therefore, we can conclude that sigma ai times yi times zi, where I goes from 1 to k, is the solution to the congruent system. Now, we need to prove that it is the only solution. We can prove it by contradiction. We first assume that there are two different solutions, aka two different congruences modulo capital N to the system. We name them x and y. So our conditions are that xi is congruent to ai mod ni, and yi is also congruent to ai mod ni, for all the i's from 1 to k. Based on addition and subtraction rules of modular arithmetic, we can get that x minus y is congruent to 0 mod ni, which means ni divides x minus y. Because all the ni's are pairwise coprime, for x minus y to be the multiple of every single one of them, it needs to be product of all the ni's. Did you see anything interesting? This product is exactly our capital N per definition, meaning that x minus y is a multiple of capital N. Capital N divides x minus 1. What does that mean? You see it now? Yep, that means x needs to be congruent to y mod capital N. This is how congruences work, so if you don't know about it, no worries. More videos will come to explain the basics of modular arithmetic rules. Anyways, with x being congruent to y mod capital N, x and y are the same modulo and thus the same solution. The one and the only solution. Sheesh, that's complicated, isn't it? How many brain cells are left? Hopefully it's enough for us to go over our last section. When and how do I apply it in questions? So let's look at an example. It's a question from EMC, by the way. Let n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 43, 44 be the 79-digit number that is formed by dividing the integers from 1 to 44 in order, one after the other. What is the remainder when n is divided by 45? So first we ask ourselves, why do we want to use the Chinese remainder theorem here? Well, 45 is a pretty big number to calculate the modulo for. And it just happens that 45 is the product of 5 and 9, two coprime numbers. Wouldn't it be so much easier if we can find a congruence of this crazily large number under mod 5 and mod 9 than find a unique solution that satisfies both conditions? Alright, so it is easy to see that n mod 5 will be 4, since its unit digit is 4. Now what about mod 9? I'm sure y'all know the divisibility rule for 9, right? If not, as a reminder, if the sum of all the digits in a number is divisible by 9, aka congruent to 0 mod 9, then the number itself is divisible by 9. The sum of the digits of n will be 1 plus 2 plus 3 plus a bunch of, you know what it is, plus 9 plus 1 plus 0, which is 10, plus 1 plus 1, which is 11, and so on, until 4 plus 4. So make the calculation easier. We can find that 4 plus 4 mod 9 is basically 44 mod 9, since it is the sum of 44 digits. This applies to all the numbers from 1 to 44 here. So n will be congruent to the sum of 1 to 44 mod 9. Sum of 1 to 44. Pretty easy. 44 times 45 divided by 2 equals 990. Well, that's divisible by 9. So n is congruent to 0 mod 9. Now it's time to show the magic of the Chinese remainder theorem. We have our little n1 and n2, which are 5 and 9. Our conditions are x is congruent to 4 mod 5 and congruent to 0 mod 9. We follow our procedure. First, to find y1 and y2. y1 equals capital N, which is 5 times 9 equals 45, divided by 5 equals 9. So y1 is 9. y2 equals capital N divided by 9, which equals 5. Then we try to find z1 and z2. z1 times y1, which is 9, equals 1 mod 5. So z1 is negative y. Similarly, z2 times y2, which is 5, equals 1 mod 9. So z2 equals 2. Now we can get our x. Sum of a1 times y1 times z1 and a2 times y2 times z2 mod capital N. It equals 4 times 9 times negative 1 plus 0 times 5 times 2 mod 45, which equals negative 36 mod 45, which is congruent to 9 mod 45. So yep, we got it. The remainder when n is divided by 45 is 9. From this example, we can see that we use Chinese remainder theorem when both the numerator and the denominator are crazily large numbers. We try to find the factors of the denominator that are pairwise coprime, so we can find the numbers that are congruent to our numerator modulo each factor. Then we find a unique solution to the simultaneous congruent system. That will be our final answer. Well, that's a lot of brain work. Or maybe not, because I assume y'all are hella smart. Anyways, Hope you are still alive and no emotional damage is done. This brings us to the end of our video. Please ask any question and leave your thoughts about the theorem in the comments. I'll try my best with my very dead brain cells to respond to the questions. Thank you so much for watching.